Okay, so it looks like it takes us a little bit slower to arrive today, but nevertheless we will start. So we'll start with some tasks from yesterday's contest, and so yesterday the easy tasks were a little bit easier than in the days before. So I think like many teams got the easy ones. So I think I will leave them. I have updated the hints document with the hints for the task Panini from the first day, and also I put the link for the official solutions to the yesterday's contest. And unfortunately these solutions are in Polish, but still you can like figure it out a little bit, like from the mathematical notation or from using some Google Translate or something like this. I think we'll be talking today about two problems from yesterday's contest, and also from about some problems from the day 3, because in day 3 we have still 3 problems which were not solved by anyone. So I think it will be good to talk a little bit about them, because they're also interesting. Okay, so let's start from yesterday. Let's start from the task antisocial network. So it was the task F. Okay, so in this task we had undirected graph. It has around 1 million of vertices, around 1 million of edges. So like a normal sized graph, and we had many operations of one kind. We had each operation consists of the set of vertices, and for each operation we flipped the edges between every pair of vertex in the set. And by flipping the edge, we mean that if there was an edge between these vertices, now we remove this edge, and if there was no edge between them, we add one edge. So for instance, if we start with graph, like let's say it has some edges. So if we make an operation which consists of the set of these 3 vertices, then after this operation we remove these 2 edges and we add this one. So after this operation we got something like this. And again we can maybe we can have like 2 vertices in the set, and after this operation we got something like this. And maybe one more example, maybe we can take these guys. So after this operation we will get something like this. And we have a lot of these operations, and after all of these operations we are asked for every vertex in the graph whether it's isolated vertex or not. So for every vertex we are asked whether it has some edges which goes to this vertex or not. So in this graph, this is the only vertex which is isolated. the other guys have some edges. And we have to answer for every vertex whether it's isolated or not. Okay, so like the naive approach would be to just simulate the whole process, but the problem with the simulation is if we have a big set of vertices in one operation, the time to add or remove every edge is proportional to s square, if s is the number of vertices in the set. And this is a little bit too much. So from the constraints of the problem, I think there was also a limit on the total sum of the vertices in all the sets, and it was also like kind of 1 million. So we can assume that if we could get an operation of updating in time all of s instead of s squared, then probably our program should be accepted. And s square will be definitely too much if the sets are big. Okay, so how to approach this kind of problem? So so usually in these problems in which we have to like do some updates on the graph, and then we are asked about some maybe connected components between vertices, or whether vertices are isolated or not, and we are like basically asked about this yes/no questions. It's useful to see whether some kind of a randomized approach can be used. So actually, we'll be using randomized approach here, and we'll use some facts we talked about yesterday during the Courier problem. And this problem will also use some kind of randomization. We choose randomly a candidate for the leader, and then we show that after we make this process several times, the probability of error is quite small. So actually here we will do pretty much, we will show an algorithm, and the calculations of the error will be pretty much the same. Okay, so how to do this? So let's what we want to do, we would like to, for every vertex, we would like to see whether it has some edges or not. So we would like to assign to the vertex some information about the edges, but we don't want to be very precise. So we cannot afford to store all the numbers of vertices which this vertex has edges to, because then we end up with s-squared solution or something like this. So we really would like to squeeze the information about these edges into as small information as possible. So one idea is we will assign for every vertex a random bit. So either 0 or 1. Okay. So let's suppose that for every vertex we have some bit. So let's say that for vertex, this is vertex v, and for vertex v we have some bit xv, and this is from 0 to 1, and this is chosen randomly. Okay, so So let's look at the vertex in the final graph. So for this vertex, we can look at the sum of values which were assigned to the vertices which are connected by the edges. So for instance, if we have some vertex, let's say this one is vertex V. So if we calculate the sum for every edge, which is V, from V to some vertex W, and if we calculate the sum of X V, and because we will be doing this modulo 2. Okay, so if this vertex is isolated in the final graph, so what will be the outcome of this sum? It will be 0. Because if the vertex is isolated, actually the sum will be empty. So it will be 0 if the vertex is isolated. Okay, so what will happen if this vertex is not isolated? What can be the outcome of the sum? Yeah, it can be 0 or 1. We really don't control whether it's 0 or 1, but because these numbers are chosen randomly and we can say uniformly, so with probability 1/2. So it's 0 with probability 1/2 and 1 with probability 1/2. So what will be the probability of this number being 1 or 0 if the vertex is not isolated? Yes, it will be 1/2, because like for every edge which is connected to this vertex, the probability that this the number in the vertex is 1 or 0 is 1/2. So actually, and it is true for every vertex. So actually, if we sum this up modulo 2, this will get us also the probability of 1/2. So basically, what we are saying here, we would like to. So this sum is. So if the vertex is not isolated, then the sum is not equal to 0 with probability 1/2. So actually, as we remember the problem couriers, it was enough for us to have the probability that we chose that the element which we choose randomly is a leader or not. The probability of error was 1/2, at most 1/2. Here we will also have the probability of error for one vertex, 1/2. If we assume that if after the calculation of the sum, if we get 0, we say, okay, the vertex is isolated. If we get non-zero, then we say, okay, the vertex is non-isolated. So actually, if we got 1, we are sure that this vertex is not isolated. It has to be at least one edge, which is connecting this vertex to some vertex with value 1. But if we get 0, okay, we will say that probably it's isolated with probability 1/2. So how can we reduce this probability? So we will use the same trick as in the problem couriers. We will like repeat the same procedure several times for the graph, and we will get and then we will say, okay, so vertex is isolated if we get 0 in all of our procedures. So in all repetitions we get 0. So then we are pretty sure that the vertex is isolated, because then the probability of success is equal to, well, 1/2. If we perform our procedure k times, so we will get 1/2 squared, 1/2 to the power of k. This is the probability of error. So the probability of success for one vertex is 1 minus 1/2 k. Of course, still the same problem we have like in the problem couriers when we have multiple queries. Here we also have multiple queries because we need to give the correct answer for all the vertices, and we have like n of them, and it's quite a lot. But again, the probability of success will be like the probability of success for every vertex. So we need to once again raise it to the nth power. But like we said in the problem of couriers, if the number k will be like around 30, then this probability, even for the big number of n, will be like probability of success will be very big. And of course you can like tweak this this value here. Okay, so so this will work, but still we have to figure out how to calculate this sum quickly for each operation. But now this problem is not very complicated, because first of all we can calculate all of these sums. We can calculate all of these sums in the starting graph. We will just because we are summing the edges, it will take time O of m to calculate the initial sums. Okay, and what is happening next? So next, when we have some operation, we see that we are removing or adding edges to vertices, but because we are calculating this sum modulo 2, actually removal of the edge, or if we remove the edge or if we add the edge, is basically the same operation. We have to add the value of this vertex to the sum of every other vertex in this cluster. So actually, what we need to do, so for instance, for this vertex, we need to add the value of this vertex and the value of this vertex, and we need to do this for all other vertices. Thanks to this, that we are doing it modulo 2. So we can do it quite fast, because first of all we will calculate the sum of values x, w for all the vertices in the cluster. So we can so first we calculate the sum of xv for v in this set, and then so let's say that this is like some value x star, and then we see that if we want to add something to this vertex, so if we want to add to this guy, and this is like vertex v, we need to add all of the other guys. So actually this is, we need to add x star minus xv. So first of all, we calculate the sum, and it can be done in linear time. And then for every vertex we add this value, and once again this can be done in linear time. Okay, so basically that's almost the end of the algorithm. So what we so to recap what is happening here. First, we calculate these sums for every vertex in the graph. Then we perform all the operations, and during the operations we are updating these sums. And at the end, we say, okay, so the vertex is isolated with high probability if the sum is equal to 0 for the particular vertex. And now we want to repeat this operation like k times. And for every vertex, we need to store the outcomes of every phase of the algorithm. So if we have k phases, so for every vertex we need to store like the vector of all the operations of all the outcomes from the phases, or we can just store whether we get at least one value 1. If so, whether we get all zeros or we get at least one, in one phase we got 1 for this vertex, and then we can be sure that this vertex is not isolated. So basically we can like repeat the whole algorithm k times, but we can do it even more quickly, because what we did here, we choose randomly one bit of information. So actually what we can do, we can choose at one go every k bits of operation. So instead of doing like this phases, instead of doing these phases one after another, we can do all of the phases at the same time. So instead of choosing randomly one bit of information, we will choose for every vertex k bits. So these are k bits chosen randomly, and then we will perform the whole algorithm at once for every bit. And why it's advantageous for us? Well, it turns out that we can store all of these bits, not like in some kind of vector or some kind of array, but we can store them in one integer. So if for instance, if we have like 30, at most 32 bits, we can store them in one integer. If we have like up to 64 bits, we can store them in one long. So actually, for every xv, we will choose randomly a number from 0 to 2 to the power of k minus 1. And what is we can see we are doing some operations modulo 2 on these bits here. So these operations correspond to some operations on the whole integers. So like adding modulo 2 to every possible bit independently, it corresponds to some operation. This is XOR. Yes, and we used XOR before when we were dealing with the problem NIM, and basically that's it. Adding each bit independently modulo 2, it's just XORing the numbers. So actually we can do the operations on the whole world. So on the all k bits at the same time, using only one XOR operation. So actually, the time complexity of our program will not be multiplied by the number k. because we will be doing all of these phases at one go. So the program will be quite fast. And yeah, and that's the solution for this problem. Okay. Any questions? Okay. If no, then we will move to the second task from yesterday's contest, and this will be the task taxi. So the task E. Okay, so in this task we had some taxi companies. There were like 10 to the 5th of them, and each taxi company has some taxi cabs, and each taxi cab is specified by three values. First of all, for each taxi, we know the number of seats. So how many passengers can ride in a cab, and also we know the cost of the trip, and the cost of the trip is characterized by two values, SI and DI, and or SI and PI, and basically the first value is the cost of the first kilometer, and the second value is the cost of the other kilometers of the trip. So basically, the trip, so X kilometer trip costs SI plus X minus 1 times PI. So this is the cost of the trip, and this value could be like quite big, and we have multiple queries, and each query is determined by two values. We want to find the cheapest way to organize the trip for MI passengers on the distance DI. So we have some queries, and we have some, and each query is determined by MI. So this is number of passengers, and DI, this is the distance. And once again, MI and DI could be quite. Also, they are like up to 10 to the 6th, and I think these guys are like 10 to the 9th or something like this. Okay, so the task formulation is pretty much complicated because we have a lot of parameters, and basically what we are asked for every query, we have to find the cheapest cost of putting all of these passengers into the cabs. So there are some assumptions that the passengers, once the passenger is in the car, it don't change cars, and also we can like have some free seats in the car. So if we have only one cab with free spaces and we have only one passenger, it could go like in the scope. Okay, so how to approach this problem? So it looks like an optimization which deals with some version of Knapsack. So after this week, I think you will be like the masters of Knapsack problems. So actually yes. So for this problem, we will have to somehow reduce it to some kind of knapsack. But still, we have a lot of parameters here, and the numbers are not very encouraging either. But one important thing is to notice that this number Ci, so the number of passengers, is quite small. So I think we will need to somehow utilize this fact. So if we want to do some knapsack here, the first thing is we would like to see what is the weight of the objects or items and what is their cost. So this value Ci is not very fortunate because the Ci suggests cost, but actually the Ci, the number of passengers we can fit in one cab, is actually the weight of the it's the weight of the item. So usually we have some kind of bag in which we put items, and here we have a little bit different perspective because we have passengers and we would like to put them into the cars, but actually the number of passengers is the size of our bag. So basically what we are doing here, we have this number of passengers and this is the size of our bag, and now we would like to put into this bag some cars, and the size of the car is the number of seats in the car, in such a way that the cost of cars which we are put in the bag is as small as possible. And also one difference is also here that usually if we have a bag and we want to put like some items, for instance, of a maximal cost, we cannot put them too much, so we cannot extend the value, the size of the of our bag. Here we have a different problem. We would like to cover the bag with the cars. So actually we have to put items in such a way that the whole bag is covered. So basically we can use a little more space, but we would like this cost to be as small as possible. So basically what I'm saying here, we will be doing a knapsack problem. So this mi is the value j from our which we use our notation from the other lectures. So this is the value j, the size of the knapsack, and we would like to find the value j which gives us the smallest cost, but the value j must be at least mi. So we'd like to cover at least mi size of the bag, maybe a little bit more, but we would like to obtain the smallest cost. And of course, the cost of the cab is determined by Si and Pi. So this is the cost of the item. Okay, so we covered most of the parameters here. We still didn't cover di, the distance, and we still didn't we still didn't take into consideration the thing that the cost is not fixed. So normally in our knapsack problems, the cost the cost of the item was constant. Here, the cost of the item will depend on how many kilometers the people want to, how far they want to go. So basically, the cost will change with the parameter di. So for different di's, we'll get different costs of elements. So it looks like for each query, we will have to we will have to start the knapsack operations from scratch, because the cost of our items will change. But we will get to this in a minute. Okay. So because the costs are changing, we need to first of all, we would like to see how they are changed. So how to actually calculate the costs of the for the cars. So like calculating the cost for the cars, it's easy if we know the distance, because this is just this formula. But let's suppose that we calculated the costs for every possible car. So we can ask ourselves whether all these cars are actually needed or not. Because what we are having here, well, we have one more assumption. We can use the same car as many times as we want. So actually, this will be this knapsack will be unbounded. Unbounded. So we have unbounded version of our knapsack. So basically, in unbounded version, when we have two elements which has the same weight, and one of the element has smaller cost than the other, it turns out that we don't need this other element at all, because we can use because the knapsack is unbounded, we can use the elements as many times as we want. So we can use the element which has smaller cost. So if the elements have the same weight and one of them has the smaller cost, we only need the smaller one. So basically, as we can see, we can have a lot of elements, but actually the different number of weights is limited by 15. So this is important here. So actually, for every different weight, we can select one car which gives us the best cost. So actually, in our knapsack problem, we will have only 15 elements. Okay. So, but still, we need to find a fast way to get the element of the smallest cost. And this can be done by a little bit geometry, because we need to optimize some linear functions. So basically, it's good to see it on the graph. So basically, what we do here, we are fixing value c. So we are fixing the value c, the number of passengers in the car, and we are considering all the cars which have the number of seats in them equal to c. And from these cars, we would like to find the car which gives us the smallest cost of the trip. And each car is determined by these two values, si and pi. And the cost of the trip is going linearly using this equation. So basically, if we have so here we will have the kilometers, and here we will have cost. So basically, for one car, we will start at S1, and the cost will grow linearly using the function of slope P1. Okay. For some different car, maybe it will be like more costly to get into this car. So like the initial the cost of the first kilometer will be higher, but actually the cost of the next kilometers can be cheaper. So then the line will have, it will start higher, but it will have lower slope. So we see from this picture that depending on how far we would like to go, it's sometimes it's better to use the first cap, sometimes it's better to use the second one. So if we would like to go this amount of kilometers, it's best to use the first cap because it will give us the less cost. But if we are after this point of kilometers, so for instance, if we are here, it's better to use the second cap. And we can have more caps. So for instance, we can have very expensive cap which has this kind of slope. So for instance, it's not very useful, this cap. I think the slope is a little bit, in this image, it's a little bit smaller than pi, so maybe they will intersect like in the after 1 million kilometers or something like this. But again, sometimes it will be useful to use some cap, and it depends on the number of kilometers. So maybe let's see one more example. So maybe we have like S4 here, and it will go like this. So then it will be, so after this point, it will be best to use the fourth cap. So basically what we are interested in, we are interested in the lower envelope of all of these lines. Okay, so we are interested in where we have the minimum. And this lower envelope can be calculated using some basic geometric algorithms. So basically, what can we? So either we can like do some pre-processing and calculate this this lower envelope, and then if we have some fixed number of kilometers, like if we have some di, we can just do binary search over this envelope to get us the minimal cost. So basically, what I'm saying here, we can prepare this data structure for every fixed value of C. So we will have like at most 15 data structures of this kind, and each data structure will give us the information about what is the minimal cost of the cab which has which has room for C passengers for every possible distance. And if you have like 10 to the fifth queries, we can afford to. I think we can afford this to get the information in logart time. So we will get the query for the costs for all the caps in time O of log n. Okay, so this was like the geometry part of this question. So now we are answering. So these structures can be prepared at the beginning. We are just analyze all the taxes, and this can be done like in time O n log n. And now we assume that we have these data structures for all of the caps. So when we have a query, we will use we will see what is the distance from this query, and thanks to that we will get at most 15 items which we would like to put in our knapsack. So for each number of seats we will get the best cost. So now we get to the knapsack part. So in the knapsack we have C. We have C elements. And C is like less than 15, and we have room for around so M is around M, because it can be a little bit bigger. So this is like the size of knapsack. Okay, so we know how to make the knapsack algorithm because we covered it during the previous lectures. So we know what is the time complexity of the knapsack, and what it is. If you have like C elements, we have the size of knapsack is M. Yeah, it's C times M. So like standard knapsack will run in time C times M, and we have to do this for every query separately, because the cost of elements change. So this will give us the algorithm of C times M times Q, which is not very promising, because both M and Q are pretty big. So it will not run in time. Okay, so what we can do here. So actually, if you recall the first lecture, we talked about knapsacks with costs and without costs, and we talk about different variants of them. And for the knapsack without costs, we also presented a variant for unbounded knapsack where the size of the knapsack was quite big, but the elements were quite small. So actually here we have like 15 elements, but they also are quite small, because they are numbers from 1 to 15. And we didn't talk about this kind of knapsack for costs. And actually some of you came to me after the lecture and asked me whether this can be done. So do we have some algorithm in which we have the big size of knapsack, and we have small elements, and we have some algorithm for this when we have additional cost. And I said that can be done, and you can like think about it. And actually this is what we need here. So here we would like to know the fast version of knapsack when we know that the elements are quite small. So if you recall this algorithm for version when we don't have any cost, then what we did there, we took the smallest element. So we took the item with the smallest weight, and we said, okay, so basically we can use this smallest element many times, and what we are missing, we just need to get the correct reminder. So if this element was like of size 3, most of the items in the knapsack will be of size 3, and then we would use some elements to get to the correct remainder. So here we would like also do some a similar thing. We would like to select some element which is quite like the best element, and we would like to put as many of these elements in the knapsack, and then use some smaller numbers of other elements which are not so good, in order to make some corrections. So actually, this is like the main idea. The main problem here is what is the best element. So what would be the best item to use many times if we have like a huge knapsack? Yes. So actually we can here we have to like consider all the costs. So we would get so let's say that we have element which has so each element has its cost and weight. So let's say, can we do some like the standard terminology? So let's say let's just say that we have weight 1 and cost 1, and up to weight C and cost C. So we have C elements, and they have weights and they have costs. So what we like to do is take element with smallest ratio cost to weight. So if you know if you read about the knapsack before, you know that there's also like all of this we talked here. They are discrete knapsacks, so you can either you take the whole element or not. But there's also like the continuous version of knapsack, when you can like split the elements. Like you can take a half of element or something like this. And in this continuous version, you know that the greedy strategies works. You always take the most cheapest, or the more if you want to like to minimize the cost, you take them as many cheap elements as possible. And here we will do a little bit of this greedy strategy. So we will try to take as many of these elements as possible, but since we are doing the discrete version of knapsack, we will have to like do some corrections using the other elements. Okay, so basically what we would like to show that you don't have to use many of the elements which are not the smallest one. And actually we will show that you don't need to use that you have to use at most weight I of other elements. So we will use at most weight I other elements. Okay, so so if we have a big knapsack, we will like put many of this smallest element. At most this number of other elements is necessary. Okay, so why is it true? So suppose that we have some knapsack, and we put some elements, like let's say we put some different elements. Okay, so these are the weights of the elements, And let's say that these are different than this optimal, that the smallest element, and there are more than weight I of them. So all of these are not ith element, and we have like 1, 2, 3, like more than weight I. So this is more than weight I. Okay, so basically what we are having here, we have some elements, and what we can do, we will look at the prefix sums of the weights of these elements. So here we have like this will be weight 1 plus weight 2. So basically we are looking at the prefix sums of the weights. Okay, how many of these prefix sums do we have? We have more than weight I. Okay, and now we can look at this prefix sums modulo weight I. Okay, so every this number we will take modulo weight I. Okay, so how many different possibilities each number can have? Because we are taking modulo weight I, we can have at most weight I possibilities. Okay, but we have more than weight I of these numbers. So at least 2 numbers we have the same remainder modulo weight I. Okay, so let's say that maybe this number and this number, they will have the same remainder modulo weight I. So what is the difference between them? Yeah, this difference is divisible by weight I. Okay, so what we can do, we can take away all of these items and put here these items. Yes, because so we can replace them by ith item. Yeah, because the total weight of this item is divisible by weight I, so we can take an integer number of these elements of the smallest cost and replace them here. And of course, like the cost will not increase because these are the elements which has the best cost per weight. So basically, what we proved this theorem here, because we assumed that we use more than weight I of other elements, and we showed that in this case we can replace them actually by these elements. So what we show here that we can use we need to use at most weight I of our elements. Okay, so that's almost end, because what we can do here, we will calculate the knapsack only for these other elements. Okay, so these other elements we have at most 15 other elements, and also the sizes of the weights of these elements are from 1 to 15. So if we can use at most 15 elements of size 15, then our size of the knapsack could be limited by 15 squared. So actually here we will have so we will use knapsack for other elements, and in this knapsack the size of the knapsack will be c squared. Okay, and we are doing this for c elements, so the knapsack will calculating the knapsack will get us the cost of c to the power of 3 times q, something like this. Okay, so we have this knapsack for other elements, and we know if the size is big, we know that what we really need to do, we need to take the remainder of this knapsack and fill it greedily with the elements of the smallest cost. And then we have to we have to use the information from this small knapsack. Okay, and this will be the this will give us the solution which will run in time. Okay, so this is all for the taxi problem. Okay, so because we are back to the subject of knapsack algorithms, we will talk now about one more task, which asks us to actually implement some kind of knapsack. So now we will talk about the task furniture from day 3. And let's at the beginning let's recall one problem we had when we talked about the problem about the cloakroom. We said something like this: we can have a structure which calculates the knapsack for us, and we can add elements to the structure, but we don't have we really don't have operation of removing the elements. And we tried to overcome this problem with different strategies, and usually we needed to use the room in RID for some additional information, but basically we cannot use this space for the information about cost anymore. So basically, in the cloakroom problem, our knapsack was a knapsack without costs, because we used the information in RID for some other purposes to our operation of removal, of our removal operation to work. And one of the idea was to store. One of the idea was to store the number of solutions for the knapsack problem, and we see that this number of solutions allow us to answer the question about whether certain element is necessary in the optimal solution of the knapsack or not, because we could just if we asked whether some element I was necessary in the knapsack of size j, we could use the number of knapsacks which use the size dj, and corresponding number of knapsacks which has the size j minus we, when we is the weight of the ith element. So the same information we would get if we could make an operation of removal if element. So if we have knapsack which considers all the elements, and we have a knapsack which considers all of the elements except the element I, we would get the same information. And to get the information about whether the element is necessary or not, we only need to remove this one element. So we only need to remove element I. We don't need to remove more elements. And actually, now we would show a nice technique which allows us to calculate the values for the knapsack problems for every possible removal of one element. So normally you have a knapsack for elements 1 to n, but now we would like to have knapsacks for elements 1 to n without element I. So we would like to have n knapsacks. Each of the knapsacks contains all of the elements except one element, one particular element. And we will do this in such a way that we want like using the array d for the information, so we could use the array d for calculating the costs. So actually this will allow us to use the knapsacks also with costs. Okay, and how to do this? The technique is somehow looks like a divide and conquer. Basically, we will start with all the elements, and we say that these are elements which are not in the knapsack. These are not in a knapsack. Okay? And we will divide them into groups. Like, let's say we will divide them in a group which contains the first 10 elements and into group which contains the second half of elements. Okay, so let's for simplicity assume that n is a power of 2, so we can make this integer division. Okay, and still we will have this assumption that these are elements which are not in the knapsack, so we have to put the other elements in the knapsack. So basically what we will have also here, we will have the RID, and like the first RID here, it will be just like, so we will initialize empty knapsack. Okay, and here, going through this edge, we will add elements, add all of the other elements to the knapsack. So these are still not in the knapsack, but all of the other elements will be added using the normal procedure of adding the elements. And here we will add the other guys to the knapsack. So basically, we'll do this recurrence in which we will partition the elements, and all of the elements which are not in our set, we will have to add them to the knapsack. So once again, we will partition this set into 2. And here we will like have 1 to n fourth, here have like n fourth plus 1 up to n and 2. And here we still will have this RID, and here we will add these guys to the RID, and here we will add these guys. So at the end, we will end up with a knapsack. So here we will add up with only one element. And here we will end up with D, and D will have, it has all elements beside 1. So it has elements 1 to n beside 1. So in the leaves, we will get, in the leaves of this tree, we will get all the structures we are interested in. So we will get all the knapsacks without one element. So now is the question: what is the time complexity of this algorithm? Okay, so we need to see what is the time complexity of adding elements to the knapsack. So we know that adding one element costs us m, where m is the size of the knapsack, and observe that on each layer of the tree, we are adding exactly n elements. So here we are adding half of the elements, and here we are adding half of elements. So like the total time complexity on this layer of the tree is n times m. And on the second layer, we are adding 1/4, 1/4, and also here we are adding 1/4 and 1/4. So on the second layer, we also use the total time of n times m. And what is the height of the tree? It's logarithm. So in total, we will use n times logarithm n to calculate all of the knapsacks without one element. So it looks like it's better than like calculating them from scratch, because then we would use n squared times m. So so this is like the nice idea for calculating it. It also can be used to other structures, not necessarily for the knapsack. If we have some structure which allows us to do fast additions of elements, but it doesn't allow us to do removals, and we still would like to, for some reason, calculate all of these structures without one element, we can use this approach. Okay, and what is the reason to use this? Actually, this idea will be useful in the task furniture. So maybe I will leave this and okay. So in the task furniture, we had some. We have some elements. Let me see the. Okay, we have some items n items up to 500, and these elements were some kinds of furniture, and these are like the types of furniture. So so we can have once again we have multiple elements of the same type. So basically we can have like CI items of type I. So basically it will look like a bounded knapsack. So in a bounded knapsack we have a bounded number of items of certain type, and once again this using our standard terminology, this is BI. So the notation could be a little bit confusing here. And for every type, we have a cost of assembling the item we have a starting cost, and there's a story that, so this is the initial cost, and there's a story that if we are assembling the next item of the same type, we get more and more efficient during the process. So this is the initial time of assembly, and this is the speed up. So the time to assemble jth item I is AI minus j minus 1 times di. So every item of the same kind, we will assemble it faster and faster. And we are asked about what is the minimal time to assemble m items. So mi items, and these items can be of any type. So we can choose which items to assemble, and we have multiple queries here. I think the number of queries was was also like 500, and the size of the query, so MJ was around 200,000, and this could be these values could be big. Okay, so we can start by making some dynamic programming here. So usually when doing dynamic programming, if we have some items, then it's good to have one dimension of the array in the dynamic programming, which tells us how many items we already considered. So let's do something like this. So we will have like array dp. In the first coordinate we will have I, which is the number of items already considered, and because we are asked the minimum time to assemble some number of items, we will have this as the second coordinate. So basically the dpij means the minimal time to assemble j items if we consider types from 1 to I. So what can we do? So basically we have to consider how many items of type I we would like to assemble. So basically, because we are minimizing the cost, this will be the minimum. So let's say that we can take from 0 up to so how many items we can take? We can take the minimum of j, because we still need to assemble j items, and we have at most ci items of type I. So we can take minimum, and what will be the minimum of? So we are considering all of the possible numbers of element I. So rest of them will be elements from 1 to I minus 1, and we are assembling k elements, and then we need to add the time which is needed to assemble k elements of size I. But this guy can be calculated quite quickly. because if you want to assemble k elements of size I, you know that for each element you have this starting cost. So this will be so basically this will be like AI plus AI minus DI plus again and plus AI minus k minus 1 times DI. And this is arithmetic progression. Then you can like calculate this this sum, and this will be this could be calculated in constant time. Okay, and if we add boundary conditions here, we would end up in dynamic programming, which is so what is the runtime of this algorithm? Okay, so we have so in the array we have n times m. So let's say that because we will get like this dynamic dynamic array for every possible m up to like the maximal m. So we can say that all of these numbers are like limited with some number m. So we get n times m, and now we need to the time of filling one cell of the array is not constant, because we need to tackle this minimum. So what is the time of considering the minimum? It's m, because like this number could be as big as j. So actually we have the algorithm which runs in times n times m squared, which is not yet too fast. So we need to speed it up a little bit. Okay. So one of the intuition we can get here is we should somehow use this information that the assembly of the items is the time of assembly of the items is decreasing. So basically, like in real life, if we do more of the items of one kind, and each of the next item is like we do it faster, so it looks like we should use this. We should use this to our advantage. So if we did many of the items of the same kind, probably it's optimal to do them as many as possible, because the more of them we are doing, the cheaper they are become. And this is actually a good intuition. And so maybe I will use okay, I will use this part. So basically, we would like to prove that there won't be many items in which we are like for which we we assemble some number of items of this type, but we didn't assemble all of them. Okay, and we will prove actually that there can be at most one such type. So for at most one such type, we will take there will be one exceptional type, and for other types we will either assemble 0 of these elements or ci of these elements. So how can we prove this? So suppose that we have two types in which we are not making in the optimal solution for which we do not take all of them or 0. So suppose we have types I and j, and in optimal solution we take Li and Lj of them, and we have the Li is strictly between 0 and Ci, and also Lj is strictly below 0 and Cj. Okay, and we would like to show now that we can replace some items of the one of these elements with the items of the second type. So what can we see here? So like on the image, it will be something like this. We would have elements of size Ci. So like the first element will take like so some number of times. The second element will get this faster, and the third one will get even faster. And for this guy, we will have something like this. Maybe this one is long, and this one is shorter, and this one is even shorter. And okay, so we have this kind of picture. So can we replace some elements with some other elements? So let's say that this last element takes us time t1, and this element takes us time t2, and let's suppose that t1 is not greater than t2. So what element can we swap? Exactly. So because element t1 is not greater than element t2, so actually the next element here, so this next element will be also not greater than t2, because the times are only decreasing. So actually we can remove element t2 and introduce this next element from Ci, and we can do this once again if we are still not every element j was removed, and we have still some elements of I, because this guy will be even greater than t2, and this guy will be even smaller than the previous one. So we can do this as long as either we removed all elements of size of item j, or we used all elements of type I. So both of these cases will show that we have smaller number of these elements which are not either fully which are not 0 or Ci. So as long as we have these pairs, we can do the same procedure, and after all of these procedures, we will end up that we have at most one element which is for which Li is not equal to 0 or Ci. So we know. So from this we know that for every item except one, we take either 0 or CI items. Okay, so what does it mean if we can take 0 or CI? Yeah, it looks like we can reduce it to the 0-1 knapsack and not like the bounded version, because we can group all of the items of the same kind like in bundles. So we group items I, items of type I, into item of weight CI and cost and what will be the cost? Actually, the cost will be this sum we had here. So this will be the cost TI CI. So this is like the cost of assembling all of the elements of this type. So we do this grouping. So basically, what we can do here, we will do. So we will do 0-1 knapsack with costs. For groups. Okay, so what is the time complexity of this 0-1 knapsack? How many groups we have? We have n groups because we have n types of items, and actually the size of our knapsack does not change. It's still m. So we will have time O of n times m for calculating this knapsack. Okay, but this is still not the end, because in this knapsack we considered all of the groups. So we considered all of the possibilities in which we take every element, in which every item is like bundled in the group. But we see here that like this, except one is important. So we can, in the optimal solution, we can have some item which is not taken in a group. And we still have to consider this. So actually, we will iterate for every such item. So we will fix. So actually, we will fix the number I, and we will say, okay, so this type of item is not taken into a group. And then for every other items, we will bundle them into groups. And we will run the knapsack algorithm for them. Okay, so this knapsack will still need to be multiplied by n, because this is the we fix element which is not in a group. Okay, so we have a knapsack structures for all other elements, and we still need to consider how to put this element which is not in a group into the knapsack. Okay, and how to do this? How to consider this this separate element? Okay, so what you are seeing here, you are like speeding up this this part. Okay, so but we still before the speed up we still need to because we have calculated the knapsack without element I, and now we still need to like add to this knapsack values of element I. So here we have like RID, and in D and with index J we have the optimal time of assembling all the elements which are in groups, so all the elements which are not of type I. And maybe it's in optimal solution we need to add some elements of type I. So we need to consider this this also in the knapsack. And the question how to do this. Okay, binary search. Well, I don't see how it would work because, well, usually in the knapsacks you don't have like this this idea that the elements in the knapsack are in some order. Like the values in this RID usually they are not like in a certain order. They're gonna be like because of this of the discrete like the nature of the knapsack. Exactly. Actually, the time of like preparing these knapsacks is quite big. We are multiplying by m here, so actually we can try all of the possibilities for CI. Like CI must be it can be quite big, like up to 10 to the 9th, but actually like it's limited by m. It's limited by the size of the knapsack. So what we can do here, we can just try all of the possibilities. Okay, so we know that we have this. We have calculated the knapsack for all the elements except type I, and now try all possibilities for type I. So we are trying all possibilities for Li up to Ci. Actually, this in optimal solution there could be a possibility that all elements are bundled, so this must be non-strict. So if we considering Li elements of type I, then the total time is D, and we have the size of the knapsack will be J. So this time size of the knapsack will be Mi, which is in our query. So it will be Mi minus Li, because this is the number of elements we are interested in, and we have to just add the time for assembling elements of type I. So this will be Li. And this procedure will take time at most O of m, because we are going through the whole knapsack. So actually, if we do this for every possible type I, we will get multiplied by n. So in total, we still are. The time complexity is still like maximized by the part of calculating knapsacks. So the total complexity is n times m, and n is squared. Okay, but as it was pointed here, we still have this on the whiteboard. We still have this nice procedure of calculating all the knapsacks without one element, and we can do this in time n times m times log n, and this is like the problem we had here with this low complexity. Actually, this complexity comes from calculating all of the knapsacks without one element. So we can use this procedure to lower the time complexity of this algorithm. So with this divide and conquer. So with divide and conquer, we can get with time to n times m times log n. And this is the model solution for this problem. Okay, so we have still time for one problem, but before that we'll take some break. So we start the second part. Is it? It should be on. Yes. Okay. Okay. So in the second part, we will talk about the problem from day 3, the problem about the goat. Okay, so in the survey I sent you before the camp, many of you write down that you would like to get some geometry problems and some math problems. So I thought that okay, so maybe we'll so maybe let's solve some hard problem which is both math and geometry. And this is the problem about the goat. So in this problem, we have some points on the plane. And these are points when in which you have some stakes in the field. So the field is covered with grass, and you have a goat. And each day a farmer takes the goat to the field. And he choose one of the stakes and fix the goat to the stake using the rope of certain size. So the goat can eat the grass, and she's very greedy, so she eat the whole grass. She can which is within the limit of the rope. So if the goat is fastened to this pole, we know that she will eat the grass and the circle of radius, let's say L. So the grass in this circle will be eaten. And so we know the radius, we know that we have n points, and we know that we have k days. So every day the farmer goes to the field, and every day he chooses the point in which the goat is fastened randomly, and he chooses like he don't get into the consideration the previous days. So it could be that in some day the goat will be fastened to the same point. The grass grows very slowly, so we can. If the goat was in this point on day 1, we say that the grass will not recover for k days. So maybe if the goat is at the same point the second day, unfortunately for the goat, it will be no grass here. But the farmer could like take the goat on the second day and put her in different stake, and then the goat will eat this part of the field. And we are interested in how much the grass will be eaten by the goat after k days. So if in this example we would have like 2 days, and the goat will be fastened to this pole in the first day and to this one in the second day, so we know that like the total area of grass which will be eaten is just the union of these 2 circles. But this is like one possibility of choosing this poles randomly. So basically what we are asked, we have to calculate the expected area of the grass which is eaten. So calculate expected area of grass which is eaten. So there was a simple sample in the task statement. The sample was with 2 points, and if you have like 2 points, then you can consider all of the possibilities which you have. So one of the possibility is that the farmer took the goat and put her either in the first. So for both days. So we have k equal to 2 days, and we have n poles. So for both days, the goat end up being fastened to the first pole. So then, what is the area of the field which was eaten? Okay, it's pi times L squared. Okay, so this is for this possibility, and also the symmetric case when the goat was fastened to the second pole. So actually, this is like 2 possibilities out of 4. So the answer is 2/4 times this area, and you have also the possibility when the goat was fastened to different poles, and then you have something like this, and depending how far these poles are from each other, you will have to like calculate the sum of these two circles. So this will be 4 times p times something crazy. Okay, so this is like the answer for this very simple case. Okay, but the limits in these problems were pretty high. So both n and k could be up to 1000. So like going through every possibility of choosing the poles, which definitely not run in time. So even if we get even if the number of possibility were a little bit lower, so like we can go through all of them, we still have to deal with the case that we have some circles on the plane. Like we can have like multiple circles, and we will have to calculate the total area of all of these circles. It can be doable, well, but still this won't pass us this problem. So okay, so how to approach this? So first of all, let's look at if we are talking about the expected area of the grass which is eaten, this expected area consists of certain area of grass which can be eaten or not. So basically, if we look at some points in the grass, we can see whether these points are eaten or not. So for instance, if these points, these 2 points, these two are either eaten or not. Yes, because they can be either covered by this circle or not. So actually, we can like consider them at the same time. So actually, what we can do here, we can consider all of these points in this part, all of the points in this part, and all of the points in this part. And for all of these parts, we can try to calculate the probability that this part will be eaten or not. Okay, so we know that for all of the points in the one part, the probability will be the same. So actually, we can for every such part, we will be interested in probability that this part is eaten, and the area of this part. Okay, so if we partition our plane into several parts, and for every part we know the probability that it was eaten, and for every part we know the area. So what will be the expected value of the area which is eaten? Yeah. So if we have probability here, and if we have like area of the part, then we will just sum for every parts, and we'll just multiply the probability by the area, and that will be the answer. So actually here we have three problems to solve. First, we need to calculate the partition into the parts, and actually we need to see how many of these parts are we going to get, because if we get like 1 billion of parts, then we really cannot do this partition. Like we need to do some clever things. And then we need to see what is the probability, and we need to calculate the area. Okay, so let's start with the first thing. Let's see how this partition look like. So basically, what we need to do, we need to consider all of the possible circles which are and the centers of the circles are these endpoints on the plane. So we have some points, and we have a circle around. Okay, we have a circle around each point. So maybe we have. Okay, so in order to split them into the parts, into the parts, we need to, for instance, we need to know where these circles intersect. So, for instance, we need to calculate all of these points. So basically, you can test every pair of circles, and if you have two circles, it's pretty simple math to calculate the points in which these circles intersect. And how many of these points can we have? Sorry? Well, okay. So for two circles we get. Yeah. So we have like two circles. We get at most two points in which they are intersecting. So if we have n squared circles, because we have n squared pairs, so we would get at most n squared points of intersection. We got n squared intersections. Okay, and how many segments do we get? Like if we treat this as let's say that the segment is like the longest arc in the circle, which is not divided by the point. So for instance, here we have one segment. So this guy is one segment, this one is like the second segment. So how many segments can we have? Okay, so so once again it could be we should look like we should look at the circles. So if you have one circle, okay, and if it has some k intersections in the circle. So for instance, if we have this circle, it has 4 intersections. So how many segments do we have on the circle? 4. So we have this segment, we have this one, and this one. So basically, a segment is like the part of the arc between 2 intersections. Okay. So if we have n squared intersections in all of the circles, so how many segments do we have? We also have n squared segments. So basically, we have this the same number of segments as intersections, apart from some the cases when we have like circles which don't like touch anything. Then we can say that for this circle we have like no intersections but 1 segment. But basically, we have at most n squared intersections and n squared segments. Okay, so now it is the question: how many areas can we have? So the area is like the part of the field which is enclosed in some kind of a polygon using this circular segments. Okay, and yeah, and the important thing here to notice that we can have at most n squared areas. And this is like the thing which can be at first a little bit counterintuitive, because if you think like you have like multiple circles which are on top of each other, so probably the intuition could be like you can have like exponential number of these small areas, but actually that can be at most n squared. And why is that? Yeah, we can use Euler formula for polygons, or for because or for planar graphs, because we can look at this this image as a planar graph. So we have some vertices, and we have some edges between them, and we have this. If we draw a planar graph in such a way that we have no intersection edges, then we can talk about this parts of the plane which are called faces. And there's a formula which shows us the how the number of edges, the number of vertices, and the number of faces relate to each other. But the one important thing about this formula is that if we have like linear number of intersections and linear number of segments, then the number of faces is also linear. And here by linear we say that linear in terms of n squared. So if you have n squared intersections, n squared segments, then also we have n squared areas. Okay, so at least we know that like the number of areas is not so big, so at least we can like iterate over all areas, or in other ways we can actually construct this whole picture, because n is up to 1000, so n squared is not so big. Okay, so this was the first thing. The second thing is let's look at the probabilities for the areas. So let's look at for instance, let's look at this area, and let's calculate the probability pi that this area is eaten. So actually, what is the only thing on which this probability depends? Yes. So actually we this part could be eaten if one of these 2 circles will be eaten. So actually the probability, and because like these circles are indistinguishable like the probability that each circle will be eaten is, because they're like chosen uniformly, so they are really like there's no real order on them or something like this. So actually what we are interested in, we are interested how many circles are covering this part, because this is the important thing. The more circles cover the same part, like the more probably it will be that this part will be eaten. So actually it's a little bit easier to calculate what is the probability that this part will not be eaten after k days. Because what is the probability it won't be eaten after 1 day? So let's say that here this part is covered. Here we have this part is covered by 2 circles, but in general it will be covered. Let's say that this is covered by j circles. So what is the probability that this part won't be eaten after 1 day? So j divided by n means that this part will be eaten. Okay, so this is probability that it will be eaten after 1 day. So 1 minus jn is the probability that it won't be eaten. So we can raise it to the kth power, and this will be probability that this part won't be eaten after k days. So once again we can subtract it from 1, and this is the probability that this part will be eaten in some of the k days. Okay, so this is our probability pi. Okay, and what is an important thing about this probability? Actually, the important thing here is that this probability does not at all depend on how this it depends only on one thing. It depends only on j, which is like the number of circles which cover a certain area. So actually here we have a little bit more information, namely that each area which is covered by the same number of circles has the same probability. So actually this area here and this area here, because they are also covered by 2 circles, these areas will have the exact same probability. And we will be using this fact in a minute. So let's look what we have so far. So we calculated that we have at most n squared areas. For each area, if we can calculate the number of circles which enclose this area, we can calculate the probability. And we need to calculate the areas of the parts. So this task can be done in a hard way, meaning that we can use the geometry algorithms to actually construct this whole graph. And these algorithms are pretty much complicated, but they will allow us to construct the graph, and for each part to calculate the area of the part. And then it will be everything, because for each part we will have the probability, we will have the area, and we can calculate this sum. But this approach would be pretty much like quite complicated in terms of implementing this. So we know that it can be done this way, but on the contest, probably it wouldn't be a good idea to go into implementing this unless we have implemented this before and we have some pre-written code to actually tackle this kind of problem. Okay, but but actually there is a solution which solves this problem without explicitly constructing this graph. And now we will use our observation that if we want to calculate the area of the part, the only interesting thing about this part is how many circles covers this part. So actually we don't need to calculate the part of every possible area. We only need to calculate the sum of the parts which has like the same number of circle covers. So let's say that we have Sj is, or Aj is the area of parts which are covered by exactly j circles. Okay, and let's say that this probability, let's call it Pj, and Pj will be the probability of covering the part which is of eating the part which is covered by j circles. So then our answer would be, we just have to consider all possible j's, and there are at most n possibilities here, because we have at most n circles, and we'll have to multiply aj by the probability. Okay, so we still need to find a way of calculating the part which is covered by exactly j circles, and we would like to do this without really constructing the graph. So what algorithms do we know for calculating the area of some, like for instance, some polygons? If you would like to calculate the area of the polygon, you don't really you don't have to use like the whole information about the polygon. Use some smaller information. Like if you want to calculate the area, you don't really need the okay, so maybe let's look how can you calculate the area of the polygon. So let's say that we have a polygon, like the normal with normal edges, and this can be like anything. And what algorithms of calculating the area do you know? Yeah. So one of the idea is to like select any point anywhere on a plane. For instance, the good candidate will be like the center of the origin of the coordinate system, and then from this point, say the point O, we are calculating the areas of every triangle which is formed by an edge and by two lines which connects the vertices connected by this edge to the point 0. And we do this in such a way that we need the directed area of this triangle. So but the basic idea is, if if the edge is directing in the positive direction around this point O, then we add the area of this triangle with the sign plus, and if this edge is directed in the reverse direction, we will add the area of this triangle with the minus sign. So we are basically subtracting this. And if we do it like for every possible edge, then we will get the area of the polygon. And this directed version of the area of the triangle, it's can be do easily by the vector product of this of these two lines. So it's like pretty much basic stuff in geometry. So this is like one idea of doing this. The second idea of doing this is we're not going through we're not summing the triangles, but we are summing the trapeziums. Or so basically what, and maybe this is like a little bit easier to understand if you see it for the first time. So basically we will once again go through every edge of this polygon, and for every edge which goes from left to right, we will consider this quadrilateral. So we are taking okay, so we are considering this figure. We are taking the edge as the top side, and the bottom side is on this line, and we are adding the area of this part with plus. And for every edge which goes from right to left, we have a similar part, but we are adding it with the minus sign. So as you can see, if you do this summation for every possible edge which goes like from left to right, you will get this like the area of this part, and then you need to like remove the area of the part which is below the polygon. So basically the idea is the same as here, but here maybe it could be a little bit easier to understand what is really going on. And what is the main advantage of this kind of algorithm? As you can see, we do some calculations for every edge of the polygon. Okay, but because we are just summing up these calculations independently, and the sum does not depend on the order of these calculations, so actually we don't need to know the order of the edges around the border of the polygon. So if someone would give us all of the edges of the polygons and said, okay, they are like in random order, they're not so they're like in random order, we still can use this algorithm to calculate the area of the polygon, because this algorithm does not depend on the order of the edges. Okay, we need to only know that this is the set of edges for the polygon. Okay, and this will be the thing we would like to use when calculating these areas. So one thing to notice here we talked about the polygons which has each side is just a line, but if this polygon was constructed from the sides which are not lines but arcs of the circle, it doesn't really matter. Maybe the calculations of these parts would get a little bit tricky, because then if we have some arc here, let's say something like this, then this part would consist of a rectangle and some kind of a shape which is a shape of a circle. So maybe still we need to like fix a triangle here, and here you have some kind of shape which is part of a circle. So actually, like calculating the area of when your polygon is constructed from the arcs of a circle, you need to do some math here, but it's still doable, and you can calculate the area of every such part in constant time. Okay, and here actually we have some polygons which are constructed from this kind of segments, and we would like to know what are the edges of these polygons. So, for instance, we would like to know what are the edges of all the parts which are covered exactly by J circles. So how can we obtain these edges? Mm-hmm. 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 Okay. Okay. So basically, what in order to see like what edges. Okay. So I see that you are like coming to the whole algorithm, but one thing we need to know. So we can ask us a very simple question. So we have an edge, okay, and what is the what is the property of this edge in order that this edge will be like the boundary of the area covered by J circles? Well, we can for instance ask ourselves by how many circles this edge should be covered, because we can ask about how many circles cover a certain area, but we also can ask how many circles covers a certain edge. Edges or circles? Okay, so we can look at how many circles actually contain a certain edge. So, for instance, here, this edge and this one, these edges are covered by two circles. So let's say that this circle on which this edge lies is also covering this edge, but also the other circle also covered this edge. So actually this edge is covered by two circles. Okay, and these are and this one, these are the only edges which are covered by exactly two circles, and it looks like there are the edges which enclose the areas which are covered by two circles. Okay, so let's see what's happening with the edges which are contained by only one circle. So, for instance, this circle can also be treated as an edge. So actually we can like split it. If we don't want to have these special cases, then we have some edges which have no intersections between them. So we can say that for every circle we have additional intersections, like for instance in these points. It will easier our implementation. And also it will easier implementation in like figuring out which parts of circle are, what areas they have. So these edges are covered by exactly one circle, and also these edges here. Okay, these edges here, they all are covered by exactly one circle. So, so for instance, here we see that this edges covers the area which is covered by exactly one circle, but unfortunately this edges covers a little bit more area. Okay, because these edges here are not, like, they are not considered. Okay, so actually we can show that if we consider every edge which is covered by J circles, they will form some kind of polygon around the part which is covered not exactly by J circles, but with at least J circles. So these guys covers the parts which are covered by one circle, but also the parts which are covered by two circles. So actually, if we change our definition of Ij, in order that Aj is area of parts which are covered by not exactly J circles, by at least J circles, then we can like then we can change the answer. We need to just remove the part which is covered by the higher number of circles here, and we are done. Okay, so like changing this definition is very simple. Okay, so now we can show that this area of parts, so actually the polygon of parts which are covered by at least J circles, this is enclosed by edges, or by the segments covered by J circles. So in order, if we want to calculate the area of this polygon, we only need to consider the segments covered by J circles. And as we know from this, we can consider them in any order we can. So we don't have to like construct the full image in order to get like where these edges are located. We can just get them one by one, and then we will apply them to the area of these parts. So the question remains how to get these edges. So what we do, we will construct every possible segment, and for every possible segment we will also calculate how many circles covers the segment. So we can do a pretty much naive way. So we are just considering one circle. Okay, and now we will be considering all of the segments which lies on this circle. So how these segments are constructed? We need to consider every other circle which intersects this, and so every intersection looks like this. Okay, so we have some intersections with other circles. We can have other circle here, and maybe some other circle here. So we can consider every possible other circle, and we calculate what are the points of intersection. And these points are dividing our original circle into segments. Okay, and now for every segment we would like to calculate what is the number of circles which enclose this segment. So now we know that we have like this segment, this one, this one, this one, this one, and so on. And again, we can do like the naive way, like for every possible segment we can choose, we can test every circle and see how many circles cover this segment, but we can do a little bit faster here. So basically, we can do some prefix sums over the circles. So first of all, we calculate how many circles covers this point. So this can be done naively. So we are considering every possible n circles, and we calculate how many circles covers this point. And then we go through, and then for each circle we have 2 points. The first point, which will give us +1, because if we are going, so we will go from this point around the circle, and when we encounter the first intersection with some circle, we give +1. If we encounter like the last intersection, the second intersection, we give -1. So once again, here we have +1, here we have -1, +1, and -1. So as we calculate the prefix sums around the circle, we will get the number of circles intersecting every segment. So here we're starting from 0, because there are no circles intersecting this point, and as we go, if we encounter this point, we know that for this segment we have 1 circle, then we get -0, so for this segment we have 0, then we have +1, so here we have 1, then we have another +1, so here we have 2, -1, 1, and -1, 0. So actually here we can have like different corner cases. So for instance, we can have like corner case in which we have a circle which only touches the second circle. So here we have like a point which is like +1 and -1 both. Okay, and if we start in a point in which so basically, if we start in a point in which we have some circles which are covering this point, then we have to initialize it by calculating naively all of these points which are covering this point. So this will we will start from 0 here, but as I understand, you're asking what if we start in the point which is like something like this, yes? Okay, so between +1 and -1. So basically, this is the previous case, yes? Something like this. Okay. So as I said, first of all, we calculate how many circles cover this point naively. We are just iterating over possible circles, and we count how many of them we have. Okay, and we have 1. So we know that we can start from 1, counting from 1. And then we go once again around the circle, and once again we are considering pluses and minuses. Okay, so by saying the first, I mean the first when you go around this direction. So for this circle, you also have +1 here and -1 here. Okay? Yes. So basically, I start with 1 here, and I go here, and this is I get -1 here, so I get to 0. Okay, so sorry, this was the confusion here. So +1s and -1s are in this order around the circle, and so that would give us every possible segment, and every possible segment with the number of circles which intersects, which covers this segment. So for every such segment, if we found this segment around the circle, we can apply the algorithm of we will calculate how many what is the income for the AJ area which comes from this segment. And of course these segments are also like directed. So this segment is like directed from right to left, and this bottom segment is directed from left to right, or vice versa. Well, the important part is that they are directed into different directions. Okay, so what is the time complexity of this solution? So we need to consider all of the possible circles. So like we take into considerations all of the circles, and for each circle we are considering every possible circle which intersects it. So this is n squared, and also in order to make this prefix sum efficiently, we need to sort these intersections along the circle. So we need some sorting, which will get us a log n factor here. So overall, this algorithm will run in time n squared log n, and because now for every segment we are updating the area in constant time, and at the end we need only linear time over n to update this sum. And also this can be done like we can say that this can be done like in constant time, because or in time depends on k, whether we use like we can use like power function from the standard library, and it will be also fast. Okay, so this is this algorithm will run in in time n squared log n. And what is the memory complexity of this algorithm? Okay, so one idea is that we have n squared, and why is that? Okay. So basically, what we are saying here, that we have to get all the all the segments, and we have n squared segments. So that would be the truth if we had to like if you had to really construct this whole image, the whole graph. Then we will need n squared memory. But actually, we don't construct them. We don't construct it. What we are doing here, we are considering each circle separately, and then we are constructing the segments which lies on one circle. And how many of segments lies on one circle? At most n, or 2 times n, but it's linear. So actually, what we are doing, and we are doing it separately for each circle, so we don't have like we don't store all of n squared segments at one time. We just considered every n segments for each circle separately, and we can like reuse this memory. So actually the memory usage of this algorithm is linear in times n. So it's yeah, so this is like the other advantage of this algorithm over this algorithm in which we are like constructing the whole graph. Okay, so this was enough to accept this problem, but there's still one nice thing about this problem. We limited the memory to linear, but actually the thing is we can solve this problem in constant memory. Okay. Okay, so what we done here, so the memory will be constant, but the time limit will not be n squared log n, so it will be higher. Yeah, I don't keep the circles. So basically, what would I would like to consider the segments separately, it's like and independently of each other. So I can say something like this. Okay, so I'm considering this circle, and now I'm considering. So let's say I'm interested in this particular segment, this one. Okay. I would like to calculate this segment. So I know that this segment comes from the fact that my main circle intersects some other circle in this point. So I can say, okay, so this is like the starting point of this segment, and I would like to find the ending point of this segment. Okay, so so basically what I'm doing here, I'm considering my main circle and the other circle, and I'm saying, okay, I would like to find out the segment which starts here, because I know that that some segments will start here because this is an intersection point. Okay, but I don't know where this segment ends, but I can find every intersection point in this area, because I can like once again I can consider every possible circle which is not this circle or this circle. Okay, so I can consider every possible other circles, and they will get me some other intersections, and I will take the intersection which is closest to this one, and this is from this side. Okay, so this will give me the length of this segment, and also I can once again naively calculate how many circles are covering this segment, because I can test every possible circles. So this solution will run in time n to the power of 3 times log n, because I will naively test all of the other circles around this segment. But then I don't need to consider all of these. I don't need to have memory to calculate all of these guys. So actually, this will work in. This operation will work in constant memory. Well, not exactly, because we still need to hold this Rij in order for this to be efficient. But once again, we can make a loop which goes through every possible j, and we can calculate like, okay, we are now only interested in the segments which are covered by j circles. So we can like calculate every a one by one. This probably will blow up the complexity to n4 log n, something like that. Maybe it can be, I don't know whether it can be avoided or not. Maybe yes, maybe no. But so we get like quite big time complexity, but the memory complexity can be reduced to constant. Okay, so I thought that we need, yeah, actually we don't need this log n, because this log n was from the sorting part, but now we are do not sort, we just take the maximum. Yes, so you're right, we don't need log n here. Okay, so that's pretty much it. So this was the last lecture during the camp. So thank you very much for your attention. It was a pleasure to be here. And there's one thing about what we will be doing after the lunch. So there will be no additional contest today, because you still have tasks which were not solved. So you can use this time for absolving them. And I will be available for some time after the lunch. So Rodolfo, correct me if I'm wrong. We can have this open after the lunch. So we will have this auditorium, and we'll have also the labs. And I will be here like until 4 p.m. something like this. And I will be available for you for some questions or yeah. So any questions you will have, you can just approach me. I will be here. Okay, so thank you very much.